In this video, we're going to do a few problems practicing stoichiometry, where it's basically that mole-to-mole ratio. But first off, and I've got a few examples that we'll do together. But first off, this one says, how many moles of oxygen atoms are present in 2.5 moles of calcium hydroxide? So to do this one, we first need the correct formula for calcium hydroxide. So calcium, let's look over at the periodic table. It's right here. So it's in the second column of the periodic table, and it's a metal. So that means the charge on calcium would be 2 plus because it has those 2 valence electrons. It wants to lose those 2, giving it a charge of 2 plus. And hydroxide, that is a polyatomic ion. It has the formula OH and it has a charge of minus. That's one that you need to memorize. It's very, very common with acid-base chemistry because it's a base. So if you need the formula for calcium hydroxide, we would need 2 of these hydroxides with 1 calcium. So the formula would be CaOH2. And that's important because the formula is where we get that stoichiometric ratio, the mole-to-mole ratio. So actually setting up the problem, 2.5 moles of calcium hydroxide. So let's start there. 2.5 moles of calcium hydroxide. And we need to convert to moles of oxygen atoms. Now we're already in moles and we're getting to moles, so we only need 1 conversion here. But the conversion that we use is basically telling us how many moles of oxygen atoms are in 1 mole of calcium hydroxide. So for every 1 mole of calcium hydroxide, and then you just look at the formula. So we have OH2, there's 1 oxygen for each hydroxide, and because there's 2 hydroxides, that means there's 2 oxygen atoms in every 1 calcium hydroxide. So the answer here is just 2.5 times 2 be 5.0 moles of oxygen atoms. And then just in terms of sig figs, we'll pay attention to sig figs each time we do this one. 2.5 has 2 sig figs, so we have 2 sig figs with our answer. Okay, next one. It says how many grams of oxygen atoms are present in 5.00 grams of lead-2 nitrate? Okay, so to do this one, we need the correct formula for lead-2 nitrate. So lead is Pb, and it is a transition metal, or actually not quite, it's over here, but it's one of those, it's not technically a transition metal, but it is one of those metals that can have multiple charges. It's not always 1 plus or always 2 plus, which is why we have the Roman numeral right there in the name. And the Roman numeral is telling us the charge of the metal. So it's Pb2 plus. And then nitrate, that is referring to a polyatomic ion, which you need to memorize, NO3 minus. So the formula for lead-2 nitrate, since nitrate is 1 minus, we'll need 2 of them. So the formula would be Pb and then parentheses NO3 and then a 2. So we're going to start off with that. We have 5 grams, so 5.00 grams of Pb NO3 And since we're starting in grams and we need to get to grams, we're actually going to have 3 conversions. Our general game plan for problems like this, where we start with grams, we need to get to grams, is we're going to be starting off with the grams of substance A, converting that to moles of substance A using the molar mass. And then we go to moles of substance B using the mole-to-mole ratio, so stoichiometry, and then going to grams of B. So that's the general plan. So the first step, going from grams of lead-2 nitrate to moles of lead-2 nitrate, we will need the molar mass. And just as a quick refresher, how do you get the molar mass? You have to find the molar masses of the individual elements. So like lead is 207.20, oxygen is 16, nitrogen is 14, and then you add those in the correct amount. So like we have 1 lead, so we'd have 207.20 for the 1 atom of lead, and then we'd have 14.01, and there's 2 nitrogens in the lead-2 nitrate, and then 16.00 times 6, because if you look at the formula, we're going to have 6 oxygens. But that's how you add it up. And when I did that, I got 331.2. And the units on a molar mass are always grams per mole. So that means that 1 mole of lead-2 nitrate weighs 331.2 grams. But anyway, that's what goes in our first conversion. So 331, and I just wrote the wrong number, 331.2 grams of lead-2 nitrate per 1 mole of lead-2 nitrate. Okay, next up, the mole-to-mole ratio. So since we're going from lead-2 nitrate to oxygen atoms in the compound, for every 1 mole of lead-2 nitrate, there's 6 oxygen atoms. So looking at the formula, we've got 3 in nitrate, and then there's 2 nitrates. 3 times 2 is 6. So there would be 6 moles of O atoms. And then next up, we need the molar mass of oxygen. Now, we are going to use the molar mass of just oxygen, not diatomic oxygen, because they're not talking about oxygen molecules in the air. They're just asking about oxygen atoms in the compound. And as we saw earlier, looking at our periodic table, oxygen's molar mass is 16. And we want to put moles on the bottom because we need it to cancel. And we want grams of oxygen, so we'll do 16.00 grams of oxygen per 1 mole of oxygen. And then just to quickly observe how units cancel, we didn't really pay attention, or I didn't cross it out. Like in the first one, the moles of calcium hydroxide canceled there. So let's look at how units cancel here. Grams of lead nitrate cancels with grams of lead nitrate. Moles of lead nitrate cancels with moles of lead nitrate. And then moles of oxygen cancels with moles of oxygen. So that's how our units cancel. And my general advice is if your units are not canceling properly when you set up your work, then your units are technically or probably going to be wrong, and your answer is definitely wrong. But if your units are working out properly, they're canceling like they're supposed to, then your answer is probably going to be fine, given you haven't made any other mistakes like a calculator error. Anyway, doing this, so on the calculator, you've got 5 divided by 331.2 times 6 and times 16. When I did that, my calculator told me 1.449. And since this 5.0 has 3 sig figs, we're going to round this to 3 sig figs. So this molar mass had more than 3 sig figs, and this had more than 3 sig figs. And in terms of sig figs, the stoichiometry, so that's a ratio that's a perfect ratio. It's exactly 1 mole of lead-2 nitrate has exactly 6 moles of oxygen atoms. So that's not affecting our sig fig rules. But anyway, 1.449, round it down to 3 sig figs, so 1.45 grams of oxygen atoms. Okay, we got 2 more. This next one says how many grams of chlorine atoms are present in 6.25 grams of iron 3 chloride. So again, first up, we do need that correct formula. So iron is Fe, and the Roman numeral 3 is telling us that it's a 3 plus. And then chloride is referring to chlorine. That's always a 1 minus because it's a halogen. So the formula for iron 3 chloride would be FeCl3. We would need 3 chlorine to balance with that 1 iron. So we'll start off with 6.25 grams of FeCl3. And we have grams, and we're trying to get to grams, so we are going to need 3 conversions. Try to leave myself a lot of space. So the first conversion, we want to go from grams of iron 3 chloride to moles of iron 3 chloride. So that's the first step in our strategy, going from grams of substance A to moles of substance A. Next, we'd want to go from moles of iron 3 chloride to moles of chlorine atoms. So that's our second step in our strategy, going from moles of A to moles of B. And then lastly, we would want to go from moles of chlorine atoms. I asked for grams, so we're going to go to grams of chlorine atoms. And that's the last step in our general strategy, going from moles of B to grams of B. So now, what I did just now is I only filled in the units. So just observing, these are how the units are going to cancel. Grams is going to cancel, moles is going to cancel, moles is going to cancel, and we'll be left with grams of chlorine atoms, which is what you want. But now let's actually fill in the values. So molar mass of iron 3 chloride. So just quickly looking over at our periodic table, iron is right here, 55.85. Chlorine is over here, 35.45. So you'd have 55.85 plus 35.45 times 3 because there's 3 chlorines. And when I did that on my calculator, I got 162.2. And it's 162.2 grams per 1 mole. So the units of molar mass are always grams per mole. And then next conversion, so the mole to mole ratio. So for every 1 iron 3 chloride, there are 3 chlorine atoms. And then the last one, the molar mass of chlorine, so we just saw on the periodic table, is 35.45. So it's 35.45 grams of chlorine per 1 mole of chlorine. So that's your setup. So on your calculator, you do 6.25 divided by 162.2 times 3, and then times 35.45. And when I did that, my calculator told me 4.097. Now, we do want to round to 3 sig figs again, so that 6.25 has 3 sig figs, and our molar masses had more than 3 sig figs. And again, the mole to mole ratio does not count. It does not affect your sig figs. So we're going to round this to 4.10 grams of chlorine atoms. So 3 sig figs. All right, last one on this page. So it says calculate the number of hydrogen atoms in 0.35 moles of C6H12O6. And what's different about this one, it says number of hydrogen atoms, not moles or grams of. So earlier we had calculate the moles of oxygen atoms, and here it's the grams of oxygen atoms. Here it just says the number. So they actually want how many, and it's going to be some really big number because atoms are really, really tiny, and we have a thing called Avogadro's number. So we'll introduce that or review it anyway. So starting off, and we've got the formula, so we didn't have to figure out the formula. That's nice. But we have 0.350 moles of C6H12O6. And our general strategy is we're going to go from moles of the substance A to moles of B to, in this case, atoms to atoms of B. So we're going to have just 2 conversions. Now the first one, going from moles of A to moles of B. So we're going from moles of the C6H12O6 to moles of hydrogen. So in C6H12O6, for every 1 molecule of that, there are 12 hydrogens. So moles of C6H12O6 are going to cancel. And then in the second conversion, we're going to use what's called Avogadro's number. And it basically is 6.022 times 10 to the 23rd things. In this case, it'll be atoms, but it could be atoms or molecules or, it's usually just atoms or molecules, but it's just a number, but it's those things per 1 mole. So it says if you had a mole of hydrogen atoms, then you have exactly 6.022 times 10 to the 23rd. And I say exactly just now, but we know that to more sig figs, but 6.022, that's usually good enough in terms of how many sig figs we have. But it's just a number. It's just a number like 1 dozen equals 12, and a gross is 144. 1 mole is 6.022 times 10 to the 23rd. But that's the conversion we're going to use here. So we'll have 6.022 times 10 to the 23rd hydrogen atoms per 1 mole of hydrogen atoms. So I put the 6.022 on the top because I want moles of hydrogen atoms to cancel. Now, if you have just like a regular scientific calculator, or you're only working on like your phone or something, doing the exponents here can be a little bit tricky. So I'm going to offer a hint on how you can manage this on a simpler calculator. On your calculator, just do 0.350 times 12 times 6.022, and we'll leave the 10 to the 23 later. So 0.35 times 12 times 6.022, your calculator should tell you 25.2924, and I'm having more sig figs at the moment on purpose. We'll round it down once we're done. So you do that on your calculator separately, and then you just kind of tack on the 10 to the 23rd without using your calculator. You just do that. So this is on your calculator, this you added manually. And then we're going to convert this. So this is not proper scientific notation, because proper scientific notation would want the decimal point to be right there between the 2 and the 5. So what we're going to do is just convert it. And one thing that I usually do to kind of keep track of am I doing it properly is, if I'm going to make this number smaller, so I'm going to convert it from 25 to 2.5. If I make that number in front smaller, then I'm going to make the second number bigger. And it would work the other way around. If you had to make the number in front bigger, then you make the other number smaller. So 25.2924, I'm going to move the decimal one spot, and it's going to become 2.52924. So I made that number smaller. I'm going to make the 10 to the 23 bigger. So that means 23 is going to become 24. And now let's round it for sig figs. So I should have 3 sig figs, because in my original problem, 0.350, that has 3 sig figs because the first 0 before the decimal doesn't count, but the second 0 that's after the 5, that one does count. So I'm going to round this to 2.53 times 10 to the 24, and then my units are hydrogen atoms.